Good day, learners. Welcome to Technical Sciences lesson. My name is Zamisile Mdima. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. So today we're going to be looking at Term 3 content, and we're beginning it by looking at electrostatics. Okay. Now, looking at the overview of the things that we're going to be touching on, we're going to be looking at Coulomb's law, which is governing the whole of electrostatics because it's talking about charges. We're going to be looking at the electric field that is created due to the interaction of two charges. We're going to be looking at how we should be drawing electric field lines. We're going to be exploring the rules that we should be following whenever we are drawing electric field lines between the charges. We're also going to be looking at the electric field lines that are existing between parallel plates where there is a positive charge and also a negative plate. Okay, we're going to be looking at the everyday application of electrostatics. And lastly, we're going to be, as we're moving right along with all the subtopics that we've touched on, we're going to be looking at the SI unit conversions, the importance of it before we put substitutions in our calculations. We have to make sure that we do our SI unit conversions properly. Okay, so let's get started. With our introduction, I want to remind us that there are two types of charges that they are. We have positive charge and also we have negative charge. Okay, so the force between the charges can either be attractive and can be repulsive, and that depends on the types of charges that are interacting with each other. Okay, so when you have like charges interacting with each other, that should be your positive charge interacting with another positive charge. You get the force of repulsion that exists between those two charges. But if you're having a positive charge and another negative charge, okay, those are considered to be unlike charges, and therefore, because they are unlike charges, there's going to be force of attraction between them. Remember, for the force of repulsion, it has to be like charges, meaning it can be positive charge against another positive charge or a negative charge against another negative charge. Either or, that results in a force of repulsion between those charges. But if it's unlike charge, positive and another negative charge, then it results in an attractive force between those 2 point charges. Okay, now forces of attraction exist between unlike charges, like we've mentioned, your unlike being your positive charge and your negative charge. And forces of repulsion exist between the like charges being the negative charge against or interacting with another negative charge, or a positive charge interacting with another positive charge. Okay, so with the force of attraction and repulsion that we are referring to, okay, we represent it by capital letter F because it's still considered to be a force, and we use SI unit of Newton because it is still considered to be what? A force. Okay, not forgetting that a force itself is what? Is a vector. So it has to have direction and magnitude as well as direction. Right, now for the symbol of charge, we'll use a capital letter Q. Okay, and then we measure charges in coulombs. All right, capital letter C, that is the SI unit for the charge. But to represent the charge itself, it's Q, but the SI unit for measuring the charge is coulombs, which is capital letter C. That is will be abbreviated so. Now the force is measured in newtons, like we've mentioned, and then the charge is measured in what? In coulombs. Okay, so this is an overall view on all the type of wording that we're going to, or terminology that we're going to be touching on, that is very important and is fundamental to today's topic. Okay, hence we made it to be our introduction. But getting on to now Coulomb's law, which is governing electrostatic. What does it say? What does Coulomb say? Coulomb is saying the force of attraction or repulsion. And if I can pause there, force of attraction or repulsion, because now we're talking about charges, and there will be a force of attraction if we have unlike point charges, And we can have repulsion because we can have like point charges, positive charge interacting with another positive charge, or negative charge interacting with another negative charge. Okay, so Coulomb's law is saying the force of attraction or repulsion between 2 point charges is directly proportional to the product of their charges, okay, the product of their charges, and is inversely proportional to the square of the distance between them. This is best represented in a formula that is saying F is equals to K, which is representing Coulomb's constant, okay, and then Q1 multiplied by Q2 divided by R squared. Now, if we put some wording as we write our formula, you will understand that we're saying the force of attraction or repulsion, which is represented by a capital letter F, we're saying that it is directly proportional to the product. Remember, this is multiply. Charge number 1 is multiplied by charge number 2. Okay, so this is directly proportional to the what? To the product of the point charges, and inversely proportional to the what? To the squared distance between them. That means that F is directly proportional to what? To Q1 and Q2, which is multiplied, because the force of attraction or repulsion is directly proportional to the what? To the product of the charges, and it is inversely proportional to the what? To the squared distance between them. It's a squared distance between them. Okay, so it is very important to look at all the qualities or the variables that we have in this formula, one by one, so that we best understand in which SI unit do they have to come into. Okay, so let's first explore the force. The force needs to be in newtons, and it has to be in newtons, like that is the SI unit for the what? For the force. And then K is your Coulomb constant, meaning that it will be given to you at your question paper. It is a constant, it does not change. It is always 9 times 10 to the power of 9 newtons per meter squared per Coulomb squared. Now we've got charge 1 and charge 2, okay, which is measured in coulombs, okay. Most of the time it will be given to you maybe in nanocoulombs, in microcoulombs. It is very important for us to know how to convert from nanocoulombs to coulombs, or microcoulombs to coulombs, to the desired one before we even attempt to substitute. Okay, it's because now we know how our charges should be in their SI units, in their proper SI unit. Okay, and then R is representing the distance of separation between these charges. Okay, and that should be in meters. Should it be given in centimeters? Should it be given in millimeters? We should know how to move from those units that it is presented in to what? To meters. Okay, so this is Coulomb's law broken down the way we should understand it. Remember, even when you forget to state Coulomb's law by word, formula should help us to get the wording right, meaning that as we are writing the formula, we should say it out loud so that we understand, or we are able to move back to what it states in words. The force of attraction or repulsion between 2 point charges is directly proportional to the what? To the product of their charges, and inversely proportional to the squared distance between them. Okay, so that is your Coulomb's constant, right? Even if you forget your Coulomb's constant, it is always provided for you at the back of your question paper, okay? Because it's a constant, it will be always provided to you. But you just need to know that represents what, okay? So that when you are substituting, you know what that K perfectly represents. Now, we just touched on conversions. We're saying here, charged, or rather charges produced by rubbing ordinary objects. Remember, we can produce charges by rubbing on ordinary objects. How can we do that? If I take my ruler and I rub it on my wool jersey, okay, what I'm actually doing is trying to make my ruler to be charged. In fact, both objects are going to be what? Charged. How, you may ask yourself? It's because electrons get transferred from one object to another object. Remember, protons do not move. Let's go way back in grade 10 work, okay? We say all the materials that are there are consisting of an atom, okay? Because an atom is a basic building block of a material, okay? So now any material that we might have, it may be my jersey, it might be my ruler, it may be this pen. All of these things are made up of atoms. Now in these atoms, we've got protons and then we've got electrons on the outer part of this atom. Right, in this atom, inside of it, we have, so let me just say, this is my atom, and inside of it, I've got a nucleus, right? So with inside the nucleus, I find my protons, okay? So this is where protons are at. They are found trapped inside what? The nucleus. And we know that by now from grade 10 work that protons are positively charged, okay? And then on the outer shells, over here, we've got what now? Electrons that are there, okay? But now for an object to be considered to be neutral, all right, it means that it has the same number of protons, meaning that the number of protons and the number of electrons is equal, okay? But now, when I start rubbing my ruler on my woolen jersey, what's happening is that this ruler that has been having neutral state, meaning that the number of electrons and the number of protons have been equal, my electrons now get transferred from my ruler to the jersey, okay, leaving it. So it was, we are making an illustration on how it was like, okay. So let's say 2 of my electrons get transferred from my ruler to my jersey, leaving my what? My ruler to be positively charged. Why is that? Because now it has more protons than what? Than electrons. It's no longer in its neutral state, but now it has more protons because these electrons have then now been transferred from the ruler to the what? To the jersey. Okay, so now you have a ruler that is what? Positively charged. Okay, so now if you attempt then to just put pieces of paper in that practical experiment that you usually do in class, put small pieces of paper, and you put the ruler towards these pieces of paper, you will see that they'll jump onto these pieces of, to the ruler itself. Why is that? Because the negative or the electrons in the pieces of paper are being attracted to the what? To the ruler itself. Why? Because the ruler is now what? Positively charged. So what I'm trying to highlight is that in all the movement, whether the objects end up being charged positively or being charged negatively, only the electrons are the ones that are moving in that transition. The protons do not move because it is hard for them to move because they are found within the nucleus of the what? Of an atom. It is not easy for them to move because they are embedded inside the nucleus. Those that are easily jumping either or on the either side of the material are the electrons because they are not found within the nucleus itself. Okay, so making it easier for us to be able to charge ordinary objects by rubbing them. Okay, so that transfer of electrons is done by that. But now, how can then we change this amount of charges that we have accumulated through rubbing? Can be in nanocoulomb or can be in microcoulomb. Okay, now don't forget that with the electron itself, the one that is able to jump, it is charged at negative 1,602 times 10 to the power of negative 19 coulombs. Okay, so that is very important to take note of the magnitude of the what of the electron itself, the one that is able to move in between the material due to the rubbing of the what of one material against one another. Okay, so we should be able, therefore it is very important to know how to move from the nanocoulomb state to coulomb, because when we're doing our calculations, we want the charges to be in what? In coulombs, okay? Not in nanocoulombs, not in microcoulombs. Yes, they can get charged in nanocoulombs, but when we're doing our calculations, we need to be able to move from those given SI units to the proper SI unit for our calculations, okay? So multiples of the charge is very important, because now it shows us how to move from those SI units that are of the microcoulomb, of the nanocoulomb, to that of what? Of coulomb. All right. So for us to be able to move from microcoulomb, okay, we need to multiply times 10 to the power of minus 6 coulombs, okay? And then for nanocoulombs, we multiply times 10 to the power of negative 9 coulombs, okay? And then the other conversion is that of the length, okay, or rather of the distance, because now we need to be able to move, whether we are given in centimeters, in millimeters, so we need to be able to move to the desired SI unit, which is what? The meters, okay? So with that one, it is very easy, because we are just reminding each other of how we used to do it. Just to remind you, we said it's kilometers. When you are moving from a big SI unit to a smaller SI unit, you just say kilometers, and you have meters here, and then you've got centimeters, and then you have millimeters here. So over here, I've just moved from a bigger SI unit to a smaller SI unit. So because kilo means 1,000, so I have to times by 1,000 in here, and this has to be multiplied by 100, and this has to be multiplied by 10. However, if now I'm moving from a smaller SI unit and I'm moving towards a bigger SI unit, okay, because we need to know how to move forward and how to move backwards. So in this case, I'm going to use my red pen so that you can see the difference between the two, okay? And please check out my arrows as well, because now I'm moving towards the what? The bigger SI unit, okay? So we have the same factors, but now we are dividing. So it's going to be divided by 10, okay? This is going to be divided by 100, and this is going to be divided by 1,000. All right. So in any other case, maybe they're giving you something in millimeters, which is often the case. You should look at where you are, okay, and the desired SI unit is in meters, so you're coming towards here. All right. So you know that because I'm moving from a smaller SI unit, I'm moving towards a bigger SI unit, what I should be doing is what? Dividing, because the arrows that are going in that direction is division, okay? And then you look at the number of zeros that you have jumped. How many zeros did you jump? Okay, you've jumped 3. How many zeros is 3? So what do you call that? If you have like 3 zeros, it's 1,000. So you know that you need to divide by what? By 1,000, okay? I'm doing this example because our desired SI unit for the distance is meters. Maybe if you are given centimeters, then you should be moving from centimeters from here, in that case, to what? To meters. So now you are dividing by how many zeros did you jump? You jumped 2 zeros. That means you should be dividing by 100. Okay, so this is one of the ways that you can remind yourself on how to do proper conversions when it comes to distance. Right, so let's do discussion number 1, which is going to be covering what we've just talked about. So it said discussion number 1, 2-point like charges carrying charges of positive 3 microcoulomb and negative 5 microcoulomb are 2 millimeters apart right? So determine determine the magnitude of the force between them and state whether it is attractive or repulsion. Okay, so I've got 2-point charges that is given to you. It is important to write data of what you have so that you can best understand whether what is it that is given to you. Is it incorrect SI unit? So you can start questioning yourself about that one. Okay, so on these ones, it is important to highlight that this is a positive 3 microcoulomb. Okay, so it is a charge. Okay, because they did say 2-point like charges. Okay, and then carrying charges of positive 3 microcoulomb and then of negative 5 microcoulomb. Okay, those are your charges. So if you were to write the data, okay, so we do know that you have Q1 and it is what? Positive 3. Because now we don't deal with microcoulomb, we deal with coulombs. And then you ask yourself, how do I change from microcoulomb to coulomb? Okay, remember, if I can just go back to the previous slide we talked about. Remember we said microcoulomb, it is times 10 to the power of minus 6. Okay, so it is best to leave the number that is given to you like that, and then times 10 to the power of what? Of minus 6 coulomb. Okay, so in that way, you've moved from a microcoulomb to a coulomb. And then charge number 2 is negative 5 because it's still in microcoulomb. You should change it. You see, writing your data reminds you of the proper SI unit that you should be using. Okay, times 10 to the power of minus 6 coulomb. Okay, and then what is the other thing that is given to you? These 2-point charges that they tell you about, they are 2 millimeters apart. Okay, that is the distance. So distance is represented by what? By R. So this is going to be 2 millimeter. Let's just go back to the previous slide shortly. So we said as we are moving from millimeter and we are heading towards what? Meters. Can you see that we've jumped how many zeros? We've jumped 3 zeros and we're heading towards a bigger SI unit. That means we should do what? Divide. Okay, so we need to divide by what? By 1,000. All right, so that is what we are going to do here, so that we get to be using the meters. Okay, so we're going to be getting what? 0,002 meters. Okay, and if we continue to read the statement, it said now determine the magnitude of the force between them and state whether it is a force of attraction or repulsion. Okay, now we have every data that we need. It is in proper SI units, and that is why we get into using now the Coulomb's law. Okay, we use the formula, the appropriate formula. Remember, we are looking for the force, which is our unknown, and we have K, which is our Coulomb's constant. It's a constant, so it has to be 9 times 10 to the power of what? Positive 9, which is then substituted here. Let's look at the formula first, even before we can look at the substitution. Q2 over what? R2. Okay, then this is Coulomb's constant. This is charge number 1. This is charge number 2. And then divided by 0,02 squared. All right, so this is the distance, but because our formula said we should square it, that is why it is 0,02 squared. Right, so you will notice also that even though we have the signs of the charges, but we did not put them, we just said it's 3 times 10 to the power of minus 6 and negative 5, because we already know that if the charges are unlike, there's a positive and there's a negative, the force that will exist there, it's a force of what? Of attraction. So what we need now is just a matter of calculating the magnitude of this force that is there. But we do know that, because now according to the question, we had to state whether there is a force of attraction or repulsion. Due to the nature of the charges themselves, we know that there's going to be a force of what? Of attraction. All right, so now we need to calculate the magnitude. Okay, You put everything that is a numerator on top, and it gives us what? 0,135. And then we divide by a 0,02 squared, which is going to give us 33,750 Newton. And I said this is a force of attraction. How? Because of the nature of the what? Of the charges that we're interacting. We had a positive charge that is interacting with a negative charge. All right, so that's how easy it is. Remember, look at the read the statement in full, write the data that you have. So what is it that is provided to you? Is it incorrect SI unit? If it's not, then change it to the correct SI unit, okay? Then you can start using your formula, your substitution, and your answer. Looking at the nature of your charges, you can tell whether the force that will exist between these two charges will be a force of attraction or a force of what? Of repulsion. All right. So, in attempting or in trying to make you do this exercise even more or practice Coulomb's law even further, this is what I have drawn up for you. So, number one, it's activity one that I want you to attempt on your own. It says, convert the following into coulombs. All right. So you have A up until E. It's given in different SI unit, but other than what? Coulombs. So the first one is 5 nanocoulombs. Okay. The second one is 0,4 nanocoulombs. Remember, nanocoulombs is what? Times 10 to the power of minus 9. Okay. So that you are able to move from nanocoulombs to coulombs. All right. C is 1 microcoulomb, 0,2 microcoulomb, and the last one is 100 nanocoulomb. Okay. So I want you guys to be able to convert these and into proper coulombs. Number two, I want you to be able to state Coulomb's law. Remember, I said to you, even when you are writing your formula, I want you to say it out loud. The force of attraction or repulsion. Just as you are writing it, Coulomb's law, also use your formula so that if there is something that you are forgetting, that you are able to remember it using your formula, and then you can translate it in what? In words. Now, number three is your calculations now. I want you to put into test whether you are able to do calculations as we are doing it together. But now I want you to attempt it on your own. So it says calculate the electrostatic force between two charges, positive 6 nanocoulomb plus 1 nanocoulomb, if they are separated by a distance of 2 millimeters. There are a lot of things that are wrong there. There are a lot of SI units that I presented to you that shouldn't be there. So I want you to know how to convert them into proper SI unit. I want you to be able to use the correct formula, and I want you to be able to substitute correctly. Okay. Number four, what is the magnitude of the repulsive force between two pith balls? A pith ball is a small light ball that can easily be charged, that are 8 centimeters apart and have equal charges of 30 nanocoulombs. Okay. This also, I want you to be able to figure out the correct formula, to figure out the proper conversion, and then do substitution, and voila, get your proper answer. Okay. Don't forget that still a force is your vector, so it has magnitude as well as what? Direction. Meaning in this case that we have to state whether this force is a force of attraction or a force of what? Of repulsion, and also their magnitude. Right. Now, there is electric field as well. Okay. But now, how does electric field come into play, as you may ask yourself? Now, electric field is a region in space in which an electric charge will experience a force. Okay, so it is a region in space where this charge is experiencing a force, whether be it a force of attraction or be it a force of repulsion. Remember, we have dived into understanding that there will be a force of attraction if there is what? If there is unlike, okay? Force of attraction if there is unlike charges that are interacting, and there will be a force of repulsion if there is like charges, whether be it a negative charges, both of them, or positive charges, both of them. Okay? But now, we have to follow the rules of drawing for us to be able to understand the electric field better. We're represented by using the lines. Okay, now in drawing these lines, the electric field lines that they are called, okay, we should be able to follow the rules of drawing electric field lines. Okay, right. First rule: arrows on the electric field lines indicate the direction of the field. Okay, in which direction is the field directed to? Okay, the direction in which the positive charge will move if placed in the field. Okay, so arrows are important. They indicate the direction. Okay, now electric field lines point away from the positive charges and towards the negative charges. That means that if you have a positive charge that is interacting with a negative charge, so the electric field lines are always to be pointing away from the positive charge and towards the negative charge. So they are moving from the positive charge and into the negative charge. Okay, so even if you have the like charges, in terms of when there is a positive charge that is interacting with another positive charge, they will have to be moving from, because we understand that electric field lines, they move from. That means they're going to be pointing away from the positive charge. And if we have 2 point charges that are negative, that are interacting with each other, though they are negative, but we understand that the electric field lines are pointing towards so the arrows need to be pointing towards the negative charge. Okay, so direction, going back to the first rule, direction is important. Okay, third rule: field lines, electric field lines that is, are drawn closer together where the field is stronger. Okay, so where they are closer, that means the electric field strength is stronger. Okay, and when they are far apart, that means the electric field strength is what? Is weaker. All right, so field lines do not touch and do not cross each other. This is reminding me of magnetism, which we did in term 2, where we spoke about the fact that when the magnetic field lines are more concentrated at the poles and more far apart as you move towards the center of the magnet. Okay, same thing here, but now we're talking about the electric field lines, no longer magnetic field line. Electric field lines, wherever they are closer, it indicates that there is a stronger electric field. Okay, they do not touch or do not cross each other. Field lines are drawn perpendicular to a charge or charged surface, and then the greater the magnitude of the charge, the stronger the electric field. Okay, so if the charge has got a greater magnitude, that means that even the electric field around it is going to be what? To be stronger. So what we do is that we represent this by drawing more field lines around the greater charge than those charges with a smaller magnitude. Okay, so we compare which one has the bigger magnitude, and then the one with the bigger magnitude will have the stronger electric field. And when we say they're strong electric field, we mean that they are more, or the electric field lines are closer to each other. Now let's take a look at these electric field lines that we keep referring to. We're giving you different circumstances. Okay, so let's look at the first one. Okay, we have a positive charge, okay, alone. That means that you can see that the electric field lines are pointing away from. So the arrows from the charge itself, the positive charge itself, they're pointing away from the what? From the charge. And then here on the blue one, we have a negative charge, so they're pointing towards it. Okay, so those are just point charges all alone. Now on the next diagram, we've got positive and another positive. Okay, you will see that they are repelling, and by that, on repelling, they are not touching each other, because now this on this point charge is moving away the electric field lines are pointing away from the charge itself, and then on this one they're pointing away from the charge itself. Same thing, repulsion, we have a force of repulsion on the diagram. Below that one, we have a negative charges that are interacting with each other. So even though the electric field lines are pointing towards the charges, why? Because electric field lines are moving from the positive and towards the negative. Okay, but now we have the unlike charges. Remember, these are like charges, and hence the repulsion force that exists between them. Okay, so in this one we have attraction force that exists, and you can tell because now we have electric field lines moving from the positive charge to the negative charge. Okay, so they are moving. If you can look closely, we have the areas that are pointing away from the positive charge, and then here they are moving towards the negative charge. So just to put it, if you cannot look at it closely, on the white charges are referred to be the positive charges, and then the dark shaded one in the middle, they are referred to be as negative charges. Okay, so this is just an illustration of the force that exists due to the interaction of 2-point charges. Now, electric field, how can we calculate this electric field? Okay, so we'll use the formula E is equals to F over Q, and we need to know what that stands for. Right, so we have E for the electric field, we have the F for the force that exists between them, okay, and then we have Q for the charge that there is. Okay, so hence we calculate the electric field as newtons per coulomb, because now we have the force at the top, which is in newtons, and then we have at the bottom at coulombs. So giving us, if we are calculating for the electric field, so it's going to be newton per coulomb. Okay, so we can write it like that, or it is like that, right? So because now we have newton per coulomb. Even right now, it is very important to take note of the proper SI unit that should be there. So that should you be given different SI units that are not required, you know that you need to do your conversions properly before you substitute. Okay. Now let's have a typical example of how we can be asked about how to calculate the electric field. Okay, we've got discussion number 2. On our discussion number 2, calculate the force experienced by Q1 if the electric field is 2 times 10 to the power of positive 3 Newton per coulomb. Okay, now we are given the electric field, all right, and then to the what? To the west, and also the direction of it. Therefore, since this, we're going to take that the west direction to be as what? To be as positive. So we're taking the side to be as positive. So if we have an answer that is giving us either or, so we take this one to be as what? To be as negative. Right. So it says that here, so we've given our charge, which is Q1, as negative 1,6 times 10 to the power of what? Of negative 19 coulombs. All right. So how do we then do this? We say, okay, we need to calculate the electric field. Which formula will give us what we want? By writing the data first. So in our data, you ask yourself, what is it that is given to me? What is it that I want? Okay, so you say, okay, I don't have the force, and it's what the question wants. Calculate the force. Calculate the force that is experienced by this charge Q1. Okay, so it's what I'm looking for. I have the what? The electric what? The electric field as 2 times 10 to the power of what? Of positive 3 Newton per coulomb. Okay, and then charge, I do have it. It is negative 1,6 times 10 to the power of 19. All right, so then from your data, you can tell that which equation will be suitable, or rather which formula will be suitable for you to be able to use. All right, so in this case, we use E is equals to F over Q. Right, we have our electric field as given, because now we're just substituting from our data that we just simplified. All right, and then is equals to F, which is the unknown, which is what we want to find out, divided by negative 1,6 times 10 to the power of negative 19, which is our charge. Okay, you do your cross multiplication because it will be looking like something like this. So E is equals to F over Q. So over here you've got 2 times 10 to the power of what? Of 3. Let me just write it clearer. Is equals to what you want over Q. So you divide this by 1 so that you cross multiply and get your answer. So F times 1 is going, then this make negative 1,6 times 10 to the power of negative 19. Okay, so 1 times F is going to give you F, and then is equals to 2 times 10 to the power of what? Of positive 3 nanocoulombs, multiplied by negative 1,6 times 10 to the power of negative 19 is therefore going to give you what? Negative 3,2 times 10 to the power of negative 16. What? Because now it is a force, it has to be in what? In Newton. Okay, so just to explain on this part that what we did was cross multiplication. All right, so it is due to the east. We'd say therefore right below that we said F is equal to therefore 3,2, because that negative is just an indication of the direction, which is what? To the east. All right, because we have already chosen the worst to be what? To be as positive. Okay, so that's how easy it is to calculate the electric field. Okay, in attempt for you to practice up until you get it right, by looking at how we did with our discussion, I want you guys to be able to do activity number 2. Okay, so let's go and read it together so that you highlight and broaden on the things that I want you to take note of. So number 1, it says calculate the electric field if a positive 5 nanocoulomb charge experiences a force of 1 times 10 to the power of negative 6 newtons. So this is what you should be able to break it down to say, okay, what is it that I have? But looking at number 1, you are given the magnitude of the charge, and you are also given the magnitude of what? Of the force. Okay, and they want you to calculate the electric field. Okay, now you write your data. In writing your data, you correct your SI unit that are not presented the way they should be. Okay, so you convert them to the proper SI unit they should be on. Okay, for example, you can see that the charge that they have given to you is a positive 5 nanocoulomb, and it should be in coulomb. So you convert that to the proper SI unit. Number 2, calculate the electric field if a negative 10 microcoulomb experiences the following forces. So you've got a 2 times 10 to the power of negative 5 newton, and you've got a 3,5 times 10 to the power of negative 6 newton to the right, and the first one to the east. Okay, so you have a charge and you have a force, and they want you to do what? To calculate the electric field. Looking at the data that you have, you choose the correct formula, you do the proper conversions, substitute, and get the correct answer with SI unit that are proper. Okay, same thing you do for number 3. Calculate the force experienced by positive 1 coulomb if it is in the following electric field. So you've got an electric field of a 10,000 newton per coulomb, and B 1,5 times 10 to the power of 3, positive 3 that is, newton per coulomb. First one has a direction of right, and the second one has got a direction of downwards. Okay, I'm sure you're going to find that very, very easy. All right, so let's move right along. One other thing I want us to touch based on is the electric field line between the parallel plates. Okay, so what you'll have is you have a plate, like it's saying, these plates are parallel to each other. So you can have positive plates at the top and then the negative plates at the bottom. So I've got a very nice diagrammatic representation of how these parallel plates exist. So you have the positive plates at the top and the negative plates at the bottom. Okay, so you have your electric field lines moving across these plates. Remember, even in parallel plates, the direction of the electric field lines is always moving from the positive plate towards the what? The negative plate, meaning that the arrows should move from the positive plate towards the what? The negative plate. Hence, you can see that the arrows in this case are facing downwards because the positive plate is at the top and the negative plate is at the bottom. Should it have been vice versa, meaning that your positive plate being at the bottom and the negative plate, that means the arrows would have been looking up direction, okay, in the north direction, that is. Okay, so we give the formula for calculating the electric field in the parallel plates because now we have a power supply that we connected to. So you'll find that these plates are then connected to the power supply. Okay, so there's a distance that exists between these two plates, and it's given in D, the small letter D. And then because there is a power supply that is needed for the electric field to start moving between these plates, so there has to be a voltage, the amount of potential difference that is given to such parallel plates for them to start functioning. Okay, so we have E is equals to V over D. But now, what do these stand for? You may ask yourself. So E is standing for the electric field in volts per meter. Okay, and we say volts per meter because right in your numerator you've got the volts, so it has to be given in volts, and then the D has to be, because it's the distance, it has to be in what? In meters. All right, hence the electric field that will exist between the parallel plates will need to be calculated in volts per meter. Okay, so that is why for our E, it is the electric field in volts per meter. V is the potential difference in volts, and the D is the distance between the plates in what? In meters. Now we've spoke about how to move from one SI unit with regards to the distance to another, so that we do proper conversions. All right, so in like any other rules, there are rules for electric field lines between parallel plates as well. Okay, so now the direction of the electric field is very important, still moving from the positive towards the negative plate. Okay, 2, the uniform electric field or a uniform electric field exists between two oppositely parallel plates. Okay, meaning that the electric field is uniform and throughout the plate itself. All right, so number 3, that leads us to number 3. The force is constant everywhere between the parallel plates. Okay, so there is uniform electric field. That means the electric field strength at any point between these parallel plates is the same. Okay, because why? Even when you are drawing them, make sure that the electric field lines are equally spaced from each other. That means if you take like 1 centimeter to write another electric field line, so it should be like that throughout your electric field plate. Why? Because we have a uniform electric field that exists there, and there's a constant force everywhere, meaning that the electric field strength experienced by at any point within, by a charge at any point within those parallel plates is the same. Okay, so those are the rules that are very much important to adhere to. But more importantly, let's touch deep on the relationship between all the variables in the formula. So remember, we have E is equals to voltage over the distance. Okay, we're saying now the electric field, which is given by capital letter E in this case, the electric field is proportional or directly proportional, I should add, directly proportional to the potential difference. That means what happens in the electric field is therefore going to have the same impact on the what? On the voltage or potential difference. Okay, so because now the electric field is directly proportional to the potential difference. As E increases, which is the electric field, also the voltage does what? Increases, and vice versa. Okay, now also the electric field is inversely proportional. The electric field is inversely proportional to the what? To the distance between them. Okay, so that means if you increase the electric field, that means the distance between them will do what? Will decrease. Okay, so and vice versa. Let's look at the electric field lines between parallel plates. How can we be asked to calculate the electric field lines between the parallel plates? So here's discussion number 3. Discussion number 3 is saying calculate the potential difference between two parallel plates if the electric field between the two parallel plates is 1,500 volts per meter and the distance between the plates is 0,01. Very crucial to write the data, because now as you are writing it, you need to remind yourself of the conversions. As you're looking at them, the electric field has correct SI unit. Okay, it should be volts per meter, and then the distance between the plates, it should be in what? In meters. So everything is all well. That means we can proceed into what? Into substitution. Okay, calculate the potential difference. That makes the V to be our unknown in the what? In the equation. Okay, just to break it down. So this is E is equals to V over D. We do have electric field, which is 1,500, is equals to what? The voltage. Okay, well, the voltage in this case is what we are looking for, over distance. Distance is what? It's is given as 0,01. Okay, and then divide this by 1 so that we are able to cross multiply. So this is going to be 1 times V, which is V, is equals to 1,500 times 0,01 is therefore going to give us what? 15. And this is 15 what? Volts. Okay, so basically what we did is to do a cross multiplication method. Right. Easy, ne? I'm sure it is. But how do I get to know that it is easier for you to? Is by when you are doing this activity 3 for me. So in this activity, I want you to practice drawing the electric field pattern between the parallel plates. Okay, so that I get to know that you understand the uniformism of the electric field in the parallel plate. I get to understand that you know the direction of the electric field lines and the proper way that it should be drawn. Okay, so we are practicing how to draw it correctly. Number 2, calculate the electric field between the two parallel plates if they are connected to a 10 volt source. Remember we said we need a power supply, okay, and are 0,15 meters apart. We have a distance, and then we are calculating what? Electric field. Don't forget data, checking your conversions, choosing your correct formula, substitution, then answer. Okay, number 3, the electric field between the two parallel plates is 2,000 volts per meter. How will the electric field change if the voltage increases, if the distance increases? So in these ones, we are exploring what you understand by the variables that are there when we say E is equal to V over D. Okay, do you understand the relationship between the electric field and the potential difference? Do you understand the relationship between the electric field and the distance between the plates? Number 4, The electric field between two parallel plates is 10,000 volts per meter. Calculate the new electric field if, okay, the voltage is doubled while keeping the distance the same. Okay, it's a question of understanding the relationship of all the variables that are there in your formula. The distance is halved while keeping the voltage constant. Okay, I know it's going to be easy for you because it's everything we've spoken about. Now, getting into real life application. Where do we use electrostatics? You may ask yourself. Now, we use technological applications of electrostatics in our photocopying machines, the photocopiers, okay? We use it for spray painting. As you see the walls that are decorated nicely using the spray paint, yes, that's where your electrostatic comes in. It's your electrostatic precipitator, it's your defibrillators, and then it's your capacitors. So these are the everyday applications of where we use our electrostatics. Okay. So today we want to end the lesson by a quote from Albert Einstein. It says that, "Oh, the only one who devotes himself to a cause with his whole strength and soul can be a true master. And for this reason, mastery demands all of a person." I'll say it again. Only one who devotes himself to a cause with his whole strength and soul can be a true master. And for this reason, mastery demands all of a person. I wish you all the best of luck as you are going to be attempting all the activities that we spoke about today. And I trust that when we meet next week, you guys are going to have done all of them and we're going to be correcting each other along the way. Okay? Have the best of the best and then goodbye.